Okay, we're back from the power outage. Where were we? Let's say we open this switch, the current stops, north pole gets weaker, which will induce a south pole on this side to oppose the loss in the north pole, which will cause the current to be induced in a clockwise direction, just as we saw here with the magnet moving away. So as the switch opens up, the light bulb will light up again, but only momentarily. Because in just a moment, the current will be stopped and it'll stay stopped. There'll be no magnetic field. There'll be no more change. So there'll be no more induced current. So it would be as if this magnet just stopped. If this magnet stops, then there won't be any more change and the current will stop. Let's see what happens if we make a graph. This is going to be current versus time in the first loop. When the switch is closed, the current will go in clockwise. Then it'll stay clockwise. When the switch is opened, then the current will diminish, but it'll still be in a clockwise direction until it stops, and then the current will stay constant, 0. So the current is 0, and now the switch closes, and the current rises rapidly. The current remains constant for a short while, and then we're going to open the switch. The current quickly drops to 0 and stays there. Now let's take a look at the current through this loop. When this switch is open and the current is 0, we'll have no current induced in this loop. Now what happens when the switch closes? The current will create a north pole here that's strengthening. This will be opposed by a current to produce a north pole here. So while this north pole is getting stronger, the current in this loop will be induced counterclockwise. Notice it's the change in current that's producing this constant counterclockwise current. Now, once this north pole reaches full strength, because the current has reached maximum value, this current stays the same. There will be no more change to oppose, and this loop will no longer have an induced current. Now, of course, when we open the switch, the north pole diminishes, and now there'll be a changing magnetic field in this coil. It's like the north pole moving away. So we're going to have an induced south pole to oppose this north pole moving away. Use the right-hand rule and you'll see the current is going now clockwise. And we have a constant current induced while this current drops off at a constant rate. In the end, the switch is open, the current is dropped to 0 and remains at 0. While it's staying at 0, that means there's no more change and the induced current drops to 0. This graph helps us see the meaning behind Lenz's law, that the induced current will be in such a direction so as to oppose the change that creates it. This is the induced current. The change is this slope. This induced current is in the opposite direction of this slope. Well, somehow that should be connected to the magnet dropping down through the big tube. Now I've got this tube hanging from a spring scale. And I'm going to drop these magnets with the batteries, make them a little heavier, down the tube. Okay, we're going to watch the value of the spring scale as this thing goes down and pops out the bottom. Here it goes. Ooh, what happened? The spring scale actually read a little less when it popped out the bottom. When it pops out the bottom, that's telling me that the magnet was inducing a current that held it back. The tube was pushing up on the magnet. Therefore, the magnet was pushing down on the tube. It weighed more. When the thing popped out the bottom, you can see it weighed less. So what does this have to do with the light bulb lighting up? Hey, it's still Lenz's law. The magnet has a velocity going down. So what will happen to a conducting ring out in front of the magnet? The current will be induced to produce a north pole, which will oppose the approaching north pole of the magnet. These two poles repel each other. The magnet will be pushing down on this loop, which is inside the metal tube. According to Newton's third law of motion, every action has an equal and opposite reaction. And this loop will be opposing the North Pole falling with this force. A free body diagram for the magnet shows us that its weight will be canceled by the magnetic force holding it up as it falls down the tube at a constant velocity. There's no acceleration. So if this magnet is being held back by this magnetic force, the magnet is pushing down on this tube. Therefore, the tube weighed more. When the magnet pops out the bottom, the tube weighed less by exactly the weight of that magnet.